Welcome to lecture number 2 for ECE 463, Modern Control, LaPlace Transforms, and Dominant Poles. Now, what we're really doing is trying to model a system. Generally, you've got an input, call it X, an output Y, and some mathematical relationship that relates X and Y. For systems, you've got static and dynamic. A static system is where the output looks just like the input. If the input's a square wave, the output's a square wave. Input's a sine wave, output's a sine wave. The only difference between the two is y is just a gain times x, say twice as big. For such a system, you can just model it with a number like 2. Output is 2 times the input. What that means is there's no memory in the system. The previous values of x and y don't matter. All that matters is the current value of x to tell you what the current value of y is. What that means is sine in gives you sine out, square wave in gives you square wave out, random number in gives you random number out. Again, they're exactly the same. For example, here's a program called VisSim. It's a program I really like. It's very similar to MATLAB's Simulink. If I take a sine wave, call it x, and then run it through a model of 2, the output in blue is twice the input. So a sine wave in gives you sine wave out. If I change this to be square wave, which is a program we don't really use too much in this class, but it is a nice system. Where's nonlinear? There it is. I can make this a square wave. So if the sine wave is positive, I get +1, negative, I get -1. Square wave in gives you square wave out. If I do a triangle wave, again, I can create a triangle wave by integrating. Block, integration, integrator. So sine wave, make it a square wave, integrate a square wave. I get a triangle wave in, triangle wave out. That's a static system. Now in contrast, a dynamic system is described by a differential equation. For dynamic systems, you need to know the initial condition. Also, dynamic systems change the shape of the input unless the input is a sine wave. So again, going back to VisSim, if I change this block, this VisSim uses the same notation as MATLAB, 1, 1, let's make 1, 2. That's decreasing powers of s, so that's 1 over s plus 2. Now if I apply a triangle wave in, the input is red, output is blue. Output's no longer a triangle wave. If I make the input a square wave, again, input is red, output is blue. Output's no longer a square wave, so I can't just simply describe this as saying the output is twice the input. It's some other relationship. That's your transfer function. This means a differential equation. Sine waves, we love and live and breathe sine waves in electrical engineering. Sine waves are eigenfunctions. It's the only function where the input and output are the same form. If the input's a 1 radian per second sine wave, the output's a 1 radian per second sine wave. It's got a different amplitude, different phase shift that leads into phasor analysis. But again, sine waves are unique. They're about the only function that has this property where the output is the same as the input. So to describe a dynamic system, I need to use differential equations. I can't just use a scalar. Now with differential equations, I can come up with a transfer function, kind of like what I just showed in VisSim. The way they relate is as follows. Assume I have x and y related by some differential equation. If I assume all functions are in the form of e to the st, then when I differentiate, I get s e to the st, or s times y. What this assumption does is it turns differential equations into algebraic equations in S, and the assumption is that algebra is easier than calculus. So let's do that. If I assume y and x are in the form of e to the st, the derivative becomes s e to the st, second derivative becomes s squared. I now factor out all the y's and x's and solve. I get a transfer function. This guy right here is the relationship between x and y. It means a differential equation. S means derivative. So if you see transfer function in S, think differential equation. To get the differential equation, go backwards. Cross multiply. S means derivative. So there's your second derivative of y. A times the first derivative, and so on. So this is the same as that differential equation. Another way of writing it. And oftentimes the differential equation is called g of s. This is essentially the gain from x to y. Again, as an example, suppose I have this differential equation. The transfer function comes from just substituting. S means derivative, so that's 3 derivatives, 2 derivatives, 1 derivative. Factor out the y, solve. Here's the relationship between x and y in transfer function form. Or the transfer function is just 20s plus 5 over s cubed plus 3s squared plus 2s plus 10. To solve for y given x, there's two main approaches. If the input is a sine wave, and sine waves are eigenfunctions. If the input's a sine wave, the output's also a sine wave in the same form. All I need to tell you is what's the amplitude and phase shift, or equally, what's the sine and cosine term. To determine that, use phasor analysis. Again, this is the gain at all frequencies. If x is 4 sine of 20t, then s is j20, that's your frequency. X is 0 minus j4, and phasor analysis, real is cosine minus j is sine, so this is 0 cosine, 4 sine. Then the output is gain times input. This is the gain everywhere. All I care about is what's the gain at s equals j20. Here's the input at j20. Output is gain times input, so y is minus 1.2 plus j.9. And what that means is the real part is cosine minus j is sine. This is y of t. And if you plot it, that's what you're going to get here. And you can check that in VisSim. Here's your simulation. I changed the input to 4 radians per second, 20 radians per second. Actually, amplitude 4 at 20 radians per second. Here's my transfer function. 200 over s squared plus 20s plus 100. Tell it to run. And the input is red, output is blue. Phasor assumes this has been true for all time, so it would be the steady state solution. Now phasors assume the input was on for all time, from time minus infinity to time plus infinity. LaPlace Transforms deals with a slightly different problem. Suppose the input turned on at t equals 0. If that's true, then the output was 0 for time less than 0. At t equals 0 it turns on and does something. That'll give you your steady state solution over here, the part that phasor gives you, plus this transient response. That transient response takes a lot of effort to find, but if you do want to find it, that's where LaPlace transforms shine. Now as comparing this class to signals and systems, modern control is actually easier than signals and systems. In signals and systems, you look at two-sided, two-dimensional LaPlace transforms. For image processing, if I have a pixel, I can go left and right. I can also go up and down. That's your two-sided, two-dimensional LaPlace transforms. In this class, your independent variable is always time. Time is a one-dimensional unidirectional vector. Time always goes forward, and there's only one dimension. I don't know what two-dimensional time is. So this class, we look at the mundane case of single-sided one-dimensional LaPlace transforms, making this class actually a lot easier than signals. And in that case, you really only need about 4 terms in your table of LaPlace transforms. The basic one is a delta function. LaPlace transform of a delta is 1. The unit step we use quite a bit. That has a LaPlace transform of 1 over s. A decaying exponential is a over s plus b. And a damped sinusoid has a complex pole. The real part is your exponential. The complex part is your frequency. From Euler's identity, do the exponential with complex terms, simplify, and it turns out that twice the amplitude is the amplitude, and the phase shift is actually the angle over the minus jc that winds up right here. So that's really all you need for LaPlace transforms in this class. To illustrate that, so I want to find the step response of the following system. Now in Math 265, you'd guess the answer, solve, take a long time. With LaPlace transforms, it's actually much easier. What I do is assume everything's in the form of e to the st. That lets you find the transfer function. Now take the Laplace transform of the input. If x is a step, that's 1 over s. So this is the Laplace transform of y. Now just find the inverse Laplace transform and you're done. The problem is this is not in my table. So what I'll do is I'll use partial fraction expansion. I've got 3 terms here. Using partial fraction, I have something over s plus 1, something over s plus 2. I like using the cover-up method. For example, the term in the middle, as s goes to minus 1, this is something over s plus 1. Pull that out. That something will be 4 over s plus 2. Evaluate at s equals minus 1, and I get minus 4. Do it for the other two terms. Take the inverse Laplace transform. These are now in my table. That's just 2 minus 4 e to the minus t plus 2 e to the minus 2t for time positive. So that's the actual response. This is what it looks like. This is also where MATLAB is really useful. I can do the same thing in MATLAB. If I, oops, go away. Clear my display. I want to input the system in MATLAB, and that system was 4 over s squared plus 3s plus 2. So g is the transfer function. 4 is the numerator. Denominator is 1, 3, 2. And input it correctly. So there's g of s. Let's take the step response for 10 seconds. T goes from 0, 0.01 to 10 seconds. Y is the step of g of s at these time points. MATLAB's now calculating y of t. And I'll plot the step response. There it is. Way, way, way easier than calculating by hand. But this is what it looks like. This is how you find out what that equation actually is. Second example. Suppose I want to find y of t when you have complex poles. Again, do the same thing we did before. X is the step input, 1 over s. Here's the transfer function. Multiply them together. That's the Laplace transform of y. To find the inverse Laplace transform, do partial fractions. And if you don't mind complex numbers, it's the same as real numbers. I just got a complex number up here. Inverse Laplace transform, this is just 1.5. Double the amplitude, I get 1.58 e to the minus t, cosine 3t, and the phase shift is over the minus j term, plus 161 degrees. Again, if we go to MATLAB, that's actually much, much easier in MATLAB. I'll input the system. G is transfer function. The numerator is 15. Denominator is 1 to 10. So there's g of s. Let's do the same time points. Find the step response, and now plot. And there's your step response. Notice it has a DC term, that's your constant 1.5, plus the decaying exponential, or decaying sine wave. That's the transient term. This guy right here. Now in terms of poles, there's a thing called a dominant pole. Poles are the energy in the system. If there's n ways to store energy, you have n poles. If there are thousands of ways to store energy, there are thousands of poles. That makes life kind of difficult. I don't want to deal with thousandth order differential equations. Fortunately, just a few poles will dominate the response, hence the name dominant pole. If I just model the dominant poles, I'll have a model which is fairly accurate, which is good. That's what I want. And also it's low order, so it's manageable, also good. So typically when we model systems, we only model the dominant poles. I don't want to deal with a thousandth order differential equation. As an example of what a dominant pole is, suppose I have two poles, one at minus 1, one at minus 10. Take the step response. If I do it by hand, I get 3 terms, the forced response and the transient response. Notice that the pole at minus 1 has the larger initial value, and it lasts longer. So I could approximate this pretty well by just saying ignore the pole at minus 10, keep this term, and the step response is close. Or another way of saying it, the second order system looks like a first order system with a pole at minus 1. That's kind of what you do with modeling. To come up with a model which is accurate but simple, come up with a model that keeps the same dominant pole, keeps the DC gain, and if you keep that, that'll behave almost the same. And if you compare the two, the second order system and the first order system, take the two step responses, they are almost identical. The whole point behind modeling is to want a model which is accurate but usable. The first order system is much more usable than the second order system. If I have 50 poles, again I might want to keep the dominant 2, throw out the past 48. Second order systems are much easier to deal with than 50th order systems. The first order approximation says if I have a dominant pole that's real, I can treat it like a first order system. If I have a first order system, I've only got 2 degrees of freedom. So given the step response, I can tell you how it's going to behave with only 2 terms. One thing kind of useful to know is the DC term. If I turn on the motor, how fast is it going to go? Plug in S equals 0, I get A over B. The 2% settling time comes from the pole. This has a pole at minus B, so when you do your partial fraction expansion, I'm going to get a term, e to the minus bt. If I say 1 is e to the minus bt 0.02, take the log. The nice thing about 0.02, the logarithm is minus 4, actually minus 3.98, pretty close to minus 4. So the settling time is just 4 over the pole. So given the transfer function, I can tell you how it's going to behave. Here's the DC gain, label the y-axis. Here's the settling time, label the x-axis, and I'm done. Pretty much all first order systems look like this. That also lets me take a complicated system like so and sketch the step response really quickly. Plug in S equals 0, the DC gain is 1.67. The dominant pole is at minus 3. So this fourth order system behaves almost the same as the first order system. Dominant pole is at minus 3. DC gain is 1.67. That's where the 5 came from. These two are almost the same. I can treat this as the first order system and sketch the step response. If I look at the actual fourth order system versus the first order systems, you can see they behave almost the same. Same settling time, same overshoot, same shape. There's a little bit of extra delay. Those poles that I ignored cause the extra delay in the system. But pretty much the first order system behaves almost the same. The dominant pole really dictates how the system is going to behave. I'd also let you go backwards. Given the step response, find the transfer function. Again, this looks like a first order system. There's no oscillations. So know it's in the form of A over S plus B. The DC gain is 4.3. The settling time is ballpark 0.53 seconds, 0.57, somewhere in here. That tells me the pole is 4 over the settling time, about minus 7. There's G of S. And notice when you find G of S, I miss the fast poles. All I capture are the dominant poles. That's first order approximations. Second order approximation. If you have 2 poles that are complex, I'll have a real part and a complex part. The complex part is the frequency of oscillation. There's their sine and cosine, 2 forms of energy bouncing back and forth, like potential energy, kinetic energy, inductor capacitance. I've got 2 energy storage elements, 2 energy states bouncing back and forth. And a real part. The real part is the exponential decay. Again, this is a sine wave that's decaying. The e to the minus sigma t is the decay. J omega t, J omega d is the frequency. So to determine how a system will behave when you have complex poles, I really need 3 parameters. One of them is the DC gain. That's G of S as S goes to 0. The other one can come from the frequency of oscillation. That's 2 pi over the period. Again, Hertz is English. Anything English is wrong. I've got to convert to radians per second. Omega d is radians per second. The settling time tells the real part of the pole. And the angle comes from the overshoot. The relationship between the overshoot, that's how big this peak is relative to DC, is e to the minus pi zeta over 1 minus zeta squared, where zeta is the damping ratio. The damping ratio is the angle of the pole. So for example, if I have this system and I want to find out what's the step response, I don't have to use MATLAB. I can tell you by inspection. Again, the dominant pole is at -1 plus J6, so the settling time is 4 over the real part, 4 seconds. The frequency of oscillation is a complex part, 6 radians per second, about 1 hertz. And the DC gain is 10.81, so I'm going to go from 0 to 10.81. To get there, I'll oscillate at 6 radians per second, and I'll decay in about 4 seconds. If I calculate overshoot in that previous equation, that also tells me that the angle of the pole corresponds to damping ratio 0.16. The damping overshoot, or the overshoot then, is 59%. I'm going to go from 0, overshoot by 59%, and then settle out at 10.81. If I check in MATLAB, I can input the system just like we did before, take the step response, and it'll look just about the same. I can also go backwards. If I'm given the step response, what's the transfer function? Again, to do that, this is a second order system. I know because it's oscillating. For that, I need 3 terms. The DC gain is 10.2-ish. The frequency of oscillation, I've got 1, 2, 3 cycles in 3.1 seconds. Tells me that the frequency of oscillation, or complex part, is 6.1. The settling time is about 5 seconds, ballpark. So the real part of the pole is 4 over 5. Putting that together, I've got a pole at 4/5, 0.8, complex parts J6.1 from mega D, and the numerator is a fudge factor, whatever it takes to make the DC gain 10.2. And for second order approximations, here's kind of a chart. If I vary the angle of the pole, zeta is the cosine of the angle. As the cosine of the angle goes between 0 and 1, the overshoot goes from no overshoot to 100% overshoot. That also affects the frequency response. I go from a low-pass filter where the gain is down 6 dB at the corner to a Butterworth filter, Chebyshev filter, then a big resonance. So that's lecture number 2 for ECE 463. Given a system, I can find the step response. Given the step response, I can find the dominant pole. And they're all done using LaPlace transforms. Also note that MATLAB is very, very useful. LaPlace transforms work, but MATLAB is a much easier way to find step responses.